Welcome back to our exploration of voltage and its role in electrical circuits. In this video, we'll dive deeper into the behavior of free electrons in conductors and how voltage establishes the flow of current. Let's start by understanding the role of free electrons. In conductive materials like copper, free electrons are always present. These electrons are not bound tightly to any single atom and can move freely within the material. Without an applied voltage, these electrons move randomly, creating no net flow or current. When voltage is applied, it establishes an electric field across the conductor. This field exerts a force on the free electrons, causing them to move from the negative terminal towards the positive terminal of the battery. This is how electron flow occurs in reality. However, in this demonstration we use conventional current, which assumes current flows from the positive terminal to the negative terminal. While this isn't how electrons physically move, conventional current remains the standard in circuit diagrams and explanations. Here's an example of a simple circuit. When the battery creates a potential difference, the excess electrons at the negative terminal are pushed through the wires and components towards the positive terminal. This flow of electrons powers devices like LEDs or motors. In this context of conventional current, this process is represented as current flowing from the positive terminal through the circuit back to the negative terminal. In an open circuit, voltage is still present at the battery terminals, but the electrons remain stationary because there's no complete path for the current to flow. Once the circuit is closed, the voltage aligns the free electrons and current flows steadily through the conductor. Using this simple circuit, we'll measure voltage with the switch in both open and closed positions. This will help us understand how potential difference is distributed and how it drives current through the circuit. Let's go step by step through the circuit, measuring voltage at key points to see how it changes when the switch is open and when it is closed. Step 1. Measuring voltage at the battery terminals. With the switch open, we place the multimeter probes directly on the battery terminals. The voltage reads approximately 12 volts, showing that the battery maintains a potential difference even when the circuit is not complete. Now with the switch closed, we measure again at the battery terminals. The voltage still reads approximately 12 volts, as the battery is designed to supply a stable potential difference to the circuit. Step 2. Measuring voltage at the fuse. At the fuse, the voltage is approximately 12 volts when the switch is open. This is because the fuse is directly connected to the battery's positive terminal and the potential difference is present at this point. When the switch is closed, the voltage at the fuse remains at 12 volts. This indicates that there is a continuous path to the positive terminal of the battery through the fuse. Step 3. Measuring voltage at the green wire leading to the latching switch. We now measure the voltage at the green wire leading into the latching switch. With the switch open, the voltage here is still approximately 12 volts, as this part of the circuit is connected to the battery's positive terminal. When the switch is closed, the voltage at the green wire remains steady at 12 volts, confirming that the potential difference continues without interruption. Step 4. Measuring voltage at the other side of the latching switch. On the opposite side of the latching switch, we see a difference. With the switch open, the voltage reads 0 volts, as the circuit is incomplete and the potential difference does not extend beyond the open switch. When the switch is closed, the voltage now reads approximately 12 volts on the other side of the switch. This indicates that the circuit is complete, and the potential difference is now present beyond this point. Step 5. Measuring voltage at the white wire leading to the LED. At the white wire leading to the LED, the voltage reads 0 volts with the switch open. Since the circuit is not complete, the potential difference doesn't reach this point. When the switch is closed, the voltage at the white wire now reads approximately 12 volts. This confirms that the potential difference has reached the LED. Step 6. Measuring the voltage at the ground side of the LED. Finally, we measure the voltage at the ground side of the LED. With the switch open, the voltage remains at 0 volts because no current is flowing and there's no potential difference on this side. When the switch is closed, the voltage on the ground side of the LED is still 0 volts. This is expected as this is a return path to the battery's negative terminal. The potential difference has been fully utilized to power the LED. These measurements highlight some key points about how voltage behaves in a circuit. Number 1, the battery maintains a consistent potential difference regardless of the circuit's state. Number 2, voltage is present up to the open point in the circuit, but cannot extend beyond it. Number 3, closing the circuit allows the potential difference to drive current through the components, powering devices like the LED. Number 4, the ground side of the circuit remains at 0 volts, completing the return path to the battery. By measuring voltage at various points in the circuit, we can better understand how potential difference drives current and diagnose any issues that might arise. In future lessons, we'll explore how resistance affects voltage and how to interpret voltage drops for troubleshooting.